Okay. In the latest release of Occult, I've included a new bit of functionality called AOTA, Asteroidal Occultation Time Analyzer. And if you go into the next slide, that's where you'll find it in Occult. It's on the Minor Planet Occultation Observations tab at the top right there. And if you go to the next slide, that's what it looks like in the raw form. And next slide. A little bit of background to what I've done here. I'm a great believer in any prediction and analysis tool of the value of having independent tools to assess things. The value of having things independent is that where the results are a little bit different, then you've got a firm basis to start looking at the two outputs that you're getting and comparing them, and then trying to figure out why they are different. One of my long-standing concerns in what we do is that the analysis stuff is rather different to prediction. On the prediction, you can generate a prediction, and the real test is when you go to the telescope, do you see an event? And if the prediction is up the creek, if the prediction is wrong, you don't see an event, and you start asking questions about, why aren't I seeing things? With analysis of light curves, the fundamental problem is you've got a data set, a single data set typically with a single light curve, which you're trying to figure out what caused it, and you've got no real way of going back and remeasuring the actual observation. You have a record, and it's how you interpret it, and how do you know whether the interpretation is right or wrong. And you can do a variety of techniques to do that, but it's a difficult problem of having confidence in the what is produced as the interpretation. And I came to the conclusion earlier this year that the best way for me to address some of my concerns in this area was actually to put the effort into write an independent bit of software to analyse light curves using different techniques to what Tony's been doing, and Tony and Bob, and just see how it compares at the end results, and have a basis for having two independent, or now three independent tools to look at this stuff, and then look at the results so that you can sit down and say, they agree, which is really good, or they don't agree, why not? And then you can start having an informed, educated discussion about the basis for the differences. So when I set out to do this, my aim was to create an alternative tool to analyse light curves. I wanted to focus on measuring the disappearance and reappearance events independently, because from my view the DNR events are statistically independent events. I wanted to make sure it could handle LiMove and Tangra files quite transparently. One of the issues there is Tangra files. There are two different formats involved with the Tangra output. Wanted to also handle output from integrating cameras so that you could, for each block of data which was integrated, have just a single data point in the analysis, and in that process to enable binning of the data. So if you've got very poor signal to noise, that at the measuring environment, you can bin the data to improve the signal to noise. I wanted to have a clear presentation of what was going on in terms of fitting, being able to see the fit of the light curve to the data points, and the final bit having user friendliness and simplicity as much as possible. Nice, noble ideas, aims and so forth, not so easy to achieve necessarily. Next slide. The basic methodology, putative events are identified using cross-correlation analysis, very much like what was done in Occultation, although I suspect I've used a different formulation of the cross-correlation expression. The disappearance and reappearance events are analysed by fitting a test light curve of varying transition durations using a chi-squared best fit analysis. The varying transitions I've worked on the basis of stellar diameter being the primary cause of any slope, and the difference between in the light curves between stellar diameter and Fresnel diffraction. Our current 8-bit video cameras are unlikely to see much difference. And the third bit is uncertainties in the event times. I determine those using a Monte Carlo analysis of the fit of the test signals to the D&R events with noise being applied to a test light curve. That's a very simple explanation of the methodology, but it's fairly comprehensive in it as well. Next slide. One of the curious things which I thought I'd briefly mention was that on the cross-correlation function and trying to look at the event times by fitting a cross-correlation function, the testing I did, I stumbled over an issue which, after you stumble over it, you look at the formula, it becomes quite apparent. But the cross-correlation function, if you're looking for a peak in the cross-correlation function, one of the things you have to be careful with is the value of the cross-correlation function has a dependency on the ratio of the duration of the occultation to the overall test signal length, which means that the cross-correlation function by itself is good but not ideal for identifying the precise event times. There's a technical issue with it. Next slide. Event identification. Some of the things I did there was that in the analysis I made sure the test signal extended for the entire duration of the recording, so that there are no issues associated with varying, having a test signal moving across the observed signal and being affected by changes in the observed signal. The test signal was fixed for the whole recording duration, and just the putative occultation is moved along that test signal. I also do a minimum cross-correlation level for a possible event. The first pass through, I say, well, what's if I say have a possible occultation of a single frame, what's the maximum value of the cross-correlation function across the whole recording? And Any real occultation's got to last for more than a single frame as a general proposition. So the any real occultation will have a cross-correlation value which is higher than that for a single frame cross-correlation function. So you can set a minimum level for which you've got a real event likely to occur. The other thing about the cross-correlation function is when you look at the nature of the occultation signal, which is effectively you got a flat signals before and after the occultation, very steep drops in and out, and flat between. That sort of, it's a very much a square function, and that leads to a very characteristic correlation function signal. It's a symmetrical triangle with straight sides, a sharp apex. It'll have a peak above the region at the bottom, which is the minimum cross-correlation level. And of course the light curve will be flat across the bottom. And if we go to the next slide, we can see what this will look like. Here's this is a light curve from the Agamemnon event. It's Anthony Talaya's observation actually, and you can see there the dots there are the individual data points from the observation. I have deliberately not joined the data points with lines because I think that's misleading as to the nature of noise. They're quite discrete data points with noise rather than the lines suggest that the signal is going from one to the other. The orange region at the bottom is sets the well, there's an orange line across the bottom which is a 0 level. The orange band across the bottom, that is the minimum level for an event which lasts for more than one frame. And then you can see how you've got the green line, it's the cross-correlation function, which is a nice apex, a triangle, sharp apex, straight sides, very symmetric. And the bottom of the light curve is fairly flat. This one, it's actually slightly U-shaped, but overall it's flat. The 5 bars across the bottom, they represent a means plus standard deviation of the mean of the 5 regions across the bottom of the light curve. And that's a very definite real occultation. If you go to the next slide, Talaya, on his observation, he had the occultation, and then shortly afterwards he had cloud move over, and this is his cloud event. And on this light curve, at the far left you can see the right hand end of the triangle from the previous event we were looking at. With this one you can see how the green line goes above the orange region, but it's not a nice triangle. The sides aren't straight, the top is not sharp, it's all rounded. And when you look at those orange regions which are across the bottom of the curve, they're not flat. It's sort of all very U-shaped. That's all symptomatic of something other than an occultation. Next slide. One of the things that I've got in this is when you measure the light curve with either Lime or Tangra, if you measure other stars, and I encourage people to measure more than just the occulted star, the other stars can be used as comparison stars, and IOTA will read any of the comparison stars which are recorded line mover will take up to 2 comparison stars, Tangra 3, and then you can selectively plot the comparison star. In this one, there's just the one comparison star. It's plotted as a green line with the data points joined together. You can see that over the first event, which is the real event, the green line is staying up at around about the same height. But over the second event, which is the cloud event, you can see how the comparison star light drops down to almost zero level, the same as the occulted star, just confirming that it was a cloud event rather than a real event. With this, as I say, you can plot up to 3 comparison stars. You can plot the data as a 5-point running average just to smooth things out a bit. You can also plot the background signal just to see what's going on there as well. Now, if we go on to the next slide. In the analysis, the cross-correlation analysis, IOTA will pick up to 5 putative events. In a normal clean occultation signal, you only get 1 putative event. In that signal from Talea, it actually pulls out 2 events. The first one is the real one, the second one is the cloudy event. But it can analyze up to 5 separate events, and you can manually decide that in all the noise you'd like to look at a point along the light curve. You can manually select an area, a point on the light curve, pick up what the cross-correlation function is saying is a possible event in that region, and analyse that as well. Rarely needed, but it's there if it's people want it. Now we go on to the next slide. This is the final slide in the presentation within IOTA as it currently exists. It's a complex slide, and I'm not going to explain all the detail in there. Firstly, this is just showing the reappearance event from Talea. You can see the blue data points stretched out quite a bit. The scale at the bottom of the plot is the frame scale, and each number increments by 10, so you're looking at a very magnified scale of the data. In the plot, there's blue and yellow regions shown in the plot, and they are defining regions which are being used to actually measure the transition. In those regions, you'll see with the data points little vertical dashed lines, and they represent the 1 standard deviation noise to be associated with the data points. So you get a sense of what is the extent of the noise which to be allocated, well, to be considered with each data point. The red lines that goes across the bottom, then almost vertical, and then across the top, there's a solid red line which is the preferred best fit, and on either side there's a dotted red line which are drawn at the uncertainty values. So you can see where the plus or minus values are fitting with the observed data points. The green line, which sort of comes down and then goes back up again, that's a curve representing the chi-squared figures for the fit of a step event to that data as you move the occultation point across. The occultation, the transition time occurs, or the best fit occurs where that curve is at a minimum point, So if you've moved the point of the occultation to the left a bit, then that green line goes up quite rapidly, telling you that that's not a very good fit. And if you go to the right, it's the same. On the bottom of the plot, the bottom right, well, bottom center is where the solution is provided. And then at the bottom right, there's two graph areas. One shows the chi-squared values, or the quality of the fit for different slopes of the transitions. And on the right-hand set of plots, that is showing the uncertainty values to be associated that comes from a Monte Carlo analysis. And that Monte Carlo analysis of these fits I found quite interesting because, and I'll show you a bit more of that in a couple of slides. To get you a bit of a sense of what you see when you analyse the data in this way, I've got about another 3 or 4 slides. We go to the next slide. This is a different event, very low signal to noise in this event, and when you look at the uncertainty range at the bottom right, when you do the Monte Carlo analysis, there are two quite discrete peaks in the uncertainty. One is at a fit at the 0 data point, and there's a separate fit, almost, well, half as good at the +3 data points, suggesting that when you look at this data point, there are in fact two quite discrete possible solutions for when the event occurred on this slight curve. One is more likely than the other, but still the second one is still quite a serious possibility. And in reporting the event times for this, you need to cover both possibilities for the event, unless you've got some way of resolving whether one of those is a false thing for some reason. It really means going back to how you measure the video. Now, if we go to the next slide, I mentioned the chi-squared curves which get plotted. The functionality that I have there is you can plot the chi-squared curves for a whole heap of the possible slopes. And here's sort of 3 typical examples of what you can see. The first one, the chi-squared curves consistently have a steep drop down to the occultation point and a steep rise up the other side. And that is a clear indication that the event time is very well defined. So you expect to have fairly small uncertainty and high confidence in the event time. The next example is interesting because you've got a steep slope on one side, but the chi-squared values on the other side of the most likely transition point are quite gentle. They don't rise up steeply at all. And this is tied in with issues of noise and stuff, but what that is suggesting is that the uncertainty on this curve, the uncertainty on the minus side is quite good, quite small, but the uncertainty on the plus side is quite large. The significant thing there is that when you're looking at a preferred time with the plus and minus uncertainties, the uncertainty values are not symmetric around the most preferred time. Now that's not something that we've catered for in our reporting processes, and something we've got to work through. Now I see Roger's asking, by uncertain, do you mean a standard deviation? Do you mean a confidence interval? The uncertainty is a confidence interval. When you do the chi-square, the Monte Carlo analysis, I guess one of the problems I have with when talking about standard deviations and stuff, we have a single observation, and to have a standard deviation with a single observation doesn't quite add up. It's really it's a confidence level of did it occur within this period before or within this period afterwards. So yes, it's not standard deviation because you have a single observation of an event, not plural observations. Now, the third example I've got there is with the chi-square curves. You can see it's a very shallow curve, and that's showing that the uncertainty is quite large. Well, it's not a well-defined event compared to the left-hand one. Now, next slide. This, from memory, is from Conard's observation of the Agamemnon event. This is, and it shows a fit of a transition of, that's a 4-frame transition. You can see the plot over 4 frames. The chi-squared plot at the bottom there, you can see how it rises and falls. A true gradual event, the plot of chi-squared rises and falls like that, whereas if it's a step event, a sudden drop, the chi-squared plot for different transitions is quite horizontal. Chi-squared is quite insensitive to the slope when the event is a sudden event, but when it's a gradual event, then a true gradual event, then you have this rise and fall quite apparent. Next slide. The output of it, I work at this stage, the event time and uncertainty I generate is entirely in context of frames, and in frames I'm really referring to the measurement units used within the analysis, which, whether it's individual fields or frames, whatever the individual measurement unit is, then that's the basis of any output that I generate. I don't get into doing subframe analysis. Values of half a frame arise because of if you have a transition occurring over an even number of frames, then the midpoint will be halfway through a frame. But that's the only basis I go into subframe analysis. I have not implemented conversion to time, and mainly because it's a very complex issue to get the time conversion. You've got to deal with camera characteristics and VTI characteristics. Terry's mentioned here, you mentioned integrating cameras. The slide I haven't shown up here is, but when you load a CSV file in, the first thing that comes up is a screen which plots the first 100 or 200 data points, and if it's an integrated camera, you have the characteristic group of data points at a single level, and with the cursor you select the start and end of that to be an integrating period, and then the program does an average of all those data and reduces all those integrated steps into a single data points, so that you finish up with a single data point for each integrated frame. Similarly, you can do the same with, you can bin data to improve signal to noise. One of the problems though is if you've got a long integration and a short recording, you can finish up not having enough data points to measure. Next slide. There's a detailed help file with step-by-step instructions and reasonable comprehensive guidance on interpreting the data. There's a fair bit of analysis to go through. And final slide. Looking at the future, possible developments of adding functionality to convert event frames to event times. I feel fairly hesitant about doing that, but a fair bit of work to achieve that. Tangra, the way IOTA has been built, it's got an interface so that measurement programs can transfer data into IOTA and then trigger the analysis of IOTA. And Risto intends on interfacing Tangra directly with IOTA so that when you measure things with Tangra, you'll be able to access the IOTA functionality, and it could be done either invisibly, so you just get the output results, or with the output displays. And enhancements of the whole system will be driven by user feedback. If no one's interested in it, then it won't go any further. If people find it useful, then we'll develop it as needed. And of course, I look forward to people comparing the results of IOTA with those with Ocular and ROTA, and debates about why the results are either the same or different. And that's the end of that presentation. Are there any questions?
They're clapping here in Canada, and they're saying, Dave, get some sleep. Very nice presentation, and thank you. Say good night, Dave. And yeah, Guy is saying good night, Dave. I think we're going to move forward to Boughton on asteroid dimensions from occultations. So if you